of an electron between neighboring ions. And that's what we call charge transfer absorption. And I think in the next slide, yeah, we have an example of that. So we have, which mineral is that? I think that's hematite, yeah. So we're looking at the spectrum, the lowermost spectrum here, which is hematite, and hematite shows both crystal field absorption features and charge transfer absorption features in the visible to near infrared. And you can see that this absorption feature here is quite broad. As we said, it needs a higher energy input to actually cause a feature, and that means we have broader, both deeper and also wider features caused by these processes. And when you compare that to a typical absorption feature happening in the shortwave infrared, yeah, it gives you a good comparison on the actual width of the feature, at least the width, but also the depth for some cases. So yeah, especially for iron oxides and rare earth elements, we will be looking for those processes, and seeing these white features in the visible to near infrared is actually quite common for any kind of oxide or hydroxide, especially for iron. And yeah, this is from the Laukam paper. So it's actually specified here, or we know quite well which energy state causes this feature, and if it's a crystal field absorption or a charge transfer absorption. And then the paper from, or the manuscript from Hunt that I just showed you in the first couple of slides, it also has quite a couple of nice tables just showing where these absorption features appear for different minerals and how wide they are. And you can see that we are also dealing with triple, like for the olivine here, which is in between the visible to near and short waves, but we'll just say in shorter wavelength ranges. There's triple features or double features, so they commonly overlap as well. And we have some of the rare earth bands here, and you can see that those are much more defined, and they give us a very different spectrum than what the charge transfer or crystal field effect is giving us, which is this very broad feature, because here we're looking at the presence of the ion and not the electron energy interaction. Yeah, so that's the process that we commonly call electronic processes. There's a couple more, but those will be better explained in different papers. And then we're dealing with vibrational processes as well. And those vibrational processes are caused by the presence of different chemical bonds. And I think I have an animation here. So what we actually look at, or what we actually call vibrational processes, are dependent on the cation and the anion and their specific weight, and how, when energy is being introduced to a system, how that causes the molecular bonds to interact. And we have stretching and bending motions mainly, and they are usually abbreviated with oh man, I wish I knew what the V meant. Let's just say V, and I know it's in one of the slides, but yeah, so we have a couple of very simple motions in that GIF that I just showed you, and those are called fundamentals. And these fundamentals usually occur after 2,700 microns, 2,700 nanometers. So they occur in the midwave and longwave infrared. But these cause vibrations and frequencies that are spilling back into the shortwave infrared. And those are usually not one overtone or one vibration, they usually overlap. So we see features that are caused by different fundamentals. So one example for H2O, in the case of, if we look at atmospheric water, there are different overtones from the OH stretch that we see here in the center, where it's very well understood that the stretch overtone is causing a feature at 1,400 nanometers, and then the hydroxide stretch causes a feature at 1,900 nanometers. And I'll just go back to this figure here, where you can see that around 1,400 nanometers, we commonly see a feature in the spectrum. Same with around 1,900 nanometers in different strengths. And that is caused by mineral-bound water, usually. It can be caused by surface water as well. That's why that region is a bit more complicated when we don't deal with very clean samples. But if we look at more standardized measurements, for example, for core scanning, then we can assume that these are usually caused by mineral-bound water, which tells us something about the mineral and not necessarily the surface state. Yeah. There's another, we can go really deep into what kind of fundamentals we have. Oh yeah, nu is the Greek letter. Nice. Okay. We could go a lot deeper into which absorption feature in which mineral is caused by which overtone and what kind of combination stretch or combination of stretching and bending. And there are a couple of really good resources for that if you're interested in one very specific mineral. I would look into how that's being affected and how different fundamentals are actually creating these absorption features. I just wanted to show you that there's a couple of fundamental stretching and bending vibrations for different molecules. And a lot of these fundamentals here are happening in the far infrared. So a lot of it is happening up to 20,000 nanometers. And what we see overlapping into what we're interested in with a linear and sphere, which can be measured in field conditions quite well, where you don't need specific instruments or correction routines. There's only a couple of these that are actually active in this wavelength region. So that will also tell us which minerals the shortwave infrared will be viable for, and which regions the midwave infrared, which minerals the midwave infrared will be viable for, and for the far infrared as well. Yeah, I'm just gonna go ahead. I'm just gonna skip ahead a little bit, but especially for the sphere active minerals, where we usually look at mineralogy and not element interactions, we have a limited window of minerals that we can map using the shortwave infrared. That's why it's very typical to map alteration mineralogy and not the main constituents of the rock, which would probably be feldspar and quartz, because those become active in the far infrared. So when you see hyperspectral maps for different deposits or different rock types, especially when it's in the linear and sphere, we usually focus on using alteration mineralogy that actually shows us the linear sphere spectrum. So it's linear sphere active, to say something about the overall rock and its position within the mineralized system. But yeah, we usually focus on some silicates, non-silicates, clay, mica, amphibole, some pyroxenes, just in broad groups. And there's a really good figure in the Trott paper that I mentioned earlier, which gives you an even better understanding of which sphere-active minerals, for example, are commonly mapped in porphyry copper deposits. And that is, already interpreted based on increasing acidity and increasing temperature to give an understanding of why specific minerals are mapped within using shortwave infrared spectroscopy, either point or imaging, and also its limits. So we usually use proxy minerals to get an understanding of a deposit instead of looking at quartz specifically or feldspar composition, for example. So those are the vibrational processes. And in this case, the Laukam paper, it does specify sphere 1 and sphere 2 range based on the two different detectors that I mentioned before here. And here the sphere 1, so the 1000 to 1800 or 1300 to 1800, usually looks at the OH overtones, hydroxyl-related stretching, and the shortwave infrared 2 between 1800 and 2600 in that case is dominated by combinations of bending and stretching, and that's what this nu and delta shows here. Again, you could go into that in a lot of detail, but there's a couple of publications where I think the processes that cause absorption features are explained quite well. and one of them is from Hunt 1982. So that's used quite a bit, has been used quite a bit since then. That's still a really good way of showing how different features are being caused. And here you see the 3 different electronic processes. We just talked about crystal field and charge transfer, but there's also color centers and conduction bands that can cause absorption features for some minerals. And then the vibrational processes, at least the overtones that we are seeing, they usually happen in the longer wavelength ranges in the shortwave infrared. Yeah, and then the last thing for today is just to look at, so what other effects on the spectrum are we experiencing? So what do we need to be cautious of when we look at a spectrum, but also what will the spectrum reveal? I think it goes both ways. So for effects on the spectrum, the mineralogy and the chemistry will influence the spectrum in most cases, or that's our assumption. There are some opaque minerals that will not be sphere active. There are some minerals that are just generally not sphere active and will show absorption features in longer or shorter wavelength ranges. But yeah, there are some influencing factors that can modify and shift absorption features, not only in brightness and contrast. And some of them are visible in the laboratory. Some of them will become more apparent when we look at field collected data, so with some atmosphere between them. But we definitely, sorry about that. We definitely have some effects on some effects of porosity that we see in the spectrum. We have effects of particle size that will affect how the scattering, how much the scattering will actually affect our spectrum. And scattering, we have different features that are caused by volume scattering or particle scattering. We have moisture content, as I showed you before, the H2O molecule or even the hydroxyl at 1,400, 1,900 will have an effect on the overall spectrum if we have a moist surface or we have water saturated samples. For example, if we look at soil samples, that will have an effect. And then apart from porosity, the surface roughness and also the viewing geometry will potentially alter our spectrum. And that becomes more interesting when we have topography, even if it's small topography within a small hand sample that we're scanning in the laboratory. We will have scattering from one surface onto another, and then potentially within a surface, if we have a very clear quartz that we look through and see a mineral through that, and information is scattered back into our camera from a mineral that is not on the surface, but under a semi-transparent one, we will see effects and we will see direct mixing of spectral features. So that's something to consider, but it's not to keep you, like, it can be really, really complex, but it's just something to keep in mind. It doesn't mean that it's too complex to get started with. Yeah. We have a couple of different mixtures that are more interesting for us when we don't look at pure samples, which is usually the case. So we can have a linear mixture between just a spatial mixture by having components present in close proximity that will fall into one pixel that we are measuring, or one field of view that we are averaging a spectra from. Then we have intimate mixtures, which is quite typical for ingrown material borders and just grain boundaries when we look at a microscopic level. Molecular mixtures and coding. And coding is especially important because hyperspectra is just a surface measure. The rule of thumb is that we will have a penetration depth of half the wavelengths. So if the longest wavelength that we are looking at is 2,500, we'll be limited to 1,200 nanometers of penetration depth. So if we have a coating like a desert varnish or something like that, that's exactly what we will see. So we need to be more aware of what we're actually measuring and what kind of how it could be a proxy for what's lying underneath. Again, that's why alteration is a big topic, to figure out the surface alteration and how that actually relies to what's underneath, and modeling based on that. spectra of rocks, I mean, we talked about minerals right now, which makes it a lot easier because we assume that a mineral is monomineralic. But once we look at rocks and rock textures, it becomes a bit more complicated. Unless we're looking at pegmatites, then we might be able to resolve the actual minerals, but we will also look at mixtures of minerals within a spectrum. I think that's quite safe to assume. So we just need to be aware that there's mixtures present. And I will talk a little bit about the different analysis types for hyperspectral data, what kind of analysis approaches there are, and some of them have unmixing in them. But yeah, we'll discuss that, especially because we're looking at rocks and not at minerals usually. Or I mean, not separately. Yeah, I just wanted to, we talked about the sphere active minerals a little bit, but one very common question when I talk to people that want to use the technology in mining or geology, but aren't aware of the limits. I think we need to be precise in that, especially the VINIA and shortwave infrared is not going to reveal sphere inactive minerals, which is feldspar, massive silica dioxide, some of the altered silica dioxide, like opal or waterbound will be visible, but most of the massive silica dioxide will not be visible. For example, for epithermal gold, we won't necessarily be able to map Waggy quartz if we're interested in that. We also need to be more precise in actual albedo or low reflectance materials because they will give us less reflected light back into our sensors, so potentially a lower signal to noise ratio to distinguish features that we're interested in. And then, unfortunately, sulfides are not something we can map directly, so we always need to find some proxy for sulfide occurrence. And there could be sulfide oxidization that we are actually mapping jarosite in areas where sulfides are present, but we just need to be aware of that. Yeah, and miraculously, I actually stuck to the time limit, so I will just stop recording. Because in the next one, we'll go into different imaging systems and more terms for spectroscopy. I realize some of that is not well understood right now, but we'll look more into the hardware part and the instrument part. That's at least what I've planned for next time. Okay, let me just stop the recording.